Hey everyone, today we're exploring the fascinating world of vectors and points within the space called Rn. That's the letter R with a superscript n. If that sounds a bit intimidating, don't worry. We're going to keep it friendly, practical, and easy to grasp with simple explanations and real-life examples. We'll also build a Python example to really bring these concepts home. What is Rn? The space Rn simply refers to an n-dimensional space where each point is represented by n real numbers. Sounds fancy? Let's simplify. R1 is a number line, just one dimension. R2 is a plane, like your computer screen or a sheet of paper, 2 dimensions. R3 is the real world around us, with length, width, and height, 3 dimensions. Higher dimensional spaces like R4, R5, and so on can't be easily visualized, but are incredibly useful in math and data science. Points versus vectors. What's the difference? Points represent locations in space. Vectors represent directions and magnitudes, like arrows pointing somewhere. Quick real-life example. Imagine you're using Google Maps. Point your home address or your favorite coffee shop, specific locations. Vector, directions like go 2 blocks east, then go 1.5 blocks south, or a step-by-step route. To keep things crystal clear, we'll follow one simple convention throughout the video. For points, we will use parentheses, round brackets. Here's an example. P equals open parentheses 3, 4, close parentheses. Here, 3 is the x-coordinate, how far you stroll right from the origin, and 4 is the y-coordinate, how high you climb up. And for vectors, we will use slightly different notation. Here's an example. Vector v equals open bracket 1, negative 2, close bracket. Here, 1 means push 1 unit along the x-axis, and negative 2 means push 2 units backward along the y-axis. Think of it as a tiny visual cue. Parentheses say, where am I? While brackets say, how do I get there? Now that we know how to read our arrows, let's talk about a super important property of those arrows. Vectors don't have a fixed position. They only care about direction and magnitude. This means that a vector like v equals vector with values 1 and 0 means go 1 unit to the right, and that's true no matter where you start. Real-life analogy. Imagine you're looking at a weather map that shows wind patterns across a city. Each little arrow on the map represents the wind vector at that location. Let's say at one point on the map, there's a wind blowing directly east at 1 km/h. That wind vector can be represented as v equals vector with values 1 and 0. Now, let's say at some other location, the wind is blowing in the exact same direction and speed. That's still the same vector v. Even though the vector is starting at a different location, it's still the same vector because it has the same direction and magnitude. Let's go back to our example. The vector v is 1, 0. This means it points 1 unit in the horizontal direction and 0 units vertically. This same vector can begin at different locations. Starting at the origin, which is 0, 0, it ends at 1, 0. Starting at the point 2, 3, it ends at 3, 3. In each case, the movement defined by the vector is identical. Only the starting point changes, not the vector itself. Let's take a look at one-dimensional space R1. Here is the example of the point P, which equals 3. Now let's take a look at vector v equals 1, meaning move 1 step forward. Here are more examples of one-dimensional vectors. Now let's take a look at different operations that we can perform over points and vectors. Vector addition, v plus w equals a vector with values v1 plus w1, v2 plus w2, and so on up to vn plus wn. The addition for vectors is an element-wise operation. For example, in 2D space, vector with values 1 and 2 plus vector with values 3 and 1 equals vector with values 4 and 3. Vector subtraction, difference in direction, v minus w equals a vector with values v minus w1, v2 minus w2, and so on up to vn minus wn. Subtraction is also an element-wise operation. Example for 2D space? We're now in 2-dimensional space R2, and we're looking at 3 vectors. First, the dark blue arrow represents vector v with values 1 and 2. This means move 1 unit to the right and 2 units up. Next, the light green arrow shows vector w with values 3 and 1. That's a movement 3 units to the right and 1 unit up. Finally, the yellow arrow represents the result of vector v minus vector w, which gives us a new vector with values -2 and 1. That means move 2 units to the left and 1 unit up. This scene nicely shows how vector subtraction gives us the direction and distance from one vector's tip to another's. In this scene, we're revisiting the result of vector subtraction, but this time by thinking of it as vector addition. We already saw how to subtract one vector from another. Here, we're doing the same thing by first finding the negative of vector w. That gives us a new vector shown in orange, with values -3 and -1 points in the exact opposite direction of vector w. Next, we add that reversed vector to vector v, which has values 1 and 2. The result, shown in yellow, is the same as before, a new vector with values -2 and 1. So subtraction, like v minus w, can also be thought of as adding v to the negative of w. The math is the same, and this picture shows how it works geometrically. A vector can be multiplied by a real number a using the following expression: a times vector v equals a vector with values a times v1, a times v2, and so on up to a times vn. Here, each element of vector v is multiplied by the number a. In this scene, we're exploring what happens when we scale vectors in two-dimensional space. We start with a collection of unit vectors, each pointing in a different direction. At the beginning, the scaling factor is 1, so all vectors stay at their original lengths. As we increase the scaling factor to 2, each vector stretches out, doubling in length, but still pointing in the same direction. Then we reduce the scaling factor to 0.5 and the vectors shrink. They still keep their original directions, but now they're only half as long. Finally, we scale up even more to a factor of 3. Now the vectors are 3 times longer than when we started, but again, the direction of each one remains unchanged. This is the key idea behind vector scaling. We change the length or magnitude of the vector, but we leave its direction exactly the same. Subtracting 2 points gives us a vector. This operation is done element by element, subtracting each coordinate of one point from the corresponding coordinate of the other. In other words, the result tells how to move from one point to the other. It gives both the direction and the distance. For example, in two-dimensional space, subtracting the point 2, 1 from the point 5, 3 gives us a vector with values 3 and 2. That means to go from home at 2, 1 to the coffee shop at 5, 3, you need to move 3 units to the right and 2 units up. Adding a vector to a point gives you a new point. This operation shifts the original point by the direction and magnitude of the vector. You simply add each coordinate of the vector to the corresponding coordinate of the point. For example, in two-dimensional space, if you start at the point 2, 1 and add the vector with values 3 and 2, you end up at a new point, 5, 3. So in real life, this is like starting at home and following a set of directions. You arrive at a new location thanks to the vector telling you how to get there. Now let's implement a simple Python class to represent vectors and perform basic operations on them like addition, subtraction, and scaling. This class is called vector. It stores coordinates and supports the following: adding 2 vectors, subtracting one vector from another, multiplying a vector by a number, reversing a vector's direction, displaying the vector in a readable format. This gives us a clean and flexible way to work with vectors using Python, just like we do in math. Now we're ready to define a class for points in space. This class is called point and models a specific location. It supports a few important geometric operations. It can be initialized with coordinates to represent a location. You can subtract one point from another to get a vector showing the direction and distance between them. You can add a vector to a point, which gives you a new point shifted by that vector. It also provides a readable description of the point. This simple example shows how we can build point and vector behavior from scratch, but in future lessons we'll rely on the NumPy library to handle vectors and matrices more efficiently. It's a powerful tool designed for fast and efficient mathematical operations, especially with vectors and arrays. Vectors and points are fundamental concepts in mathematics, programming, and even real life. Understanding how they differ and how they work together is key to solving complex problems more easily. I hope you enjoyed this quick journey into Rn, the n-dimensional space. Try experimenting with the Python code yourself. It's one of the best ways to get comfortable with these ideas. Let me know in the comments what topics you'd like to explore next. Happy coding and stay curious.